In 2013, Android Bitcoin wallets started bleeding coins. Nobody was hacked. Their phones simply picked the same random number twice. That single failure mode connects three quiet stories inside every Bitcoin signature. Why we shipped with ECDSA instead of Schnorr, how one repeated nonce drains a wallet, and how Segwit diffused a quadratic-time attack hiding inside legacy transactions. To understand how a random number can leak your keys, start with what's actually being signed. Bitcoin uses ECDSA, the elliptic curve digital signature algorithm, but Satoshi didn't pick ECDSA because it's elegant. He picked it because Schnorr signatures, the cleaner alternative invented in 1989, were locked behind a patent that didn't expire until 2008. By the time Bitcoin launched in 2009, every cryptographic library on Earth shipped ECDSA, and almost none shipped Schnorr. ECDSA was the pragmatic default, despite being more complex, nonlinear, and lacking a complete security proof, even 30 years later. Side by side, the trade-offs are stark. ECDSA requires more verification operations and has no clean security proof. Schnorr does. ECDSA is nonlinear, meaning two signatures can't simply be added together. Schnorr is linear, which is why aggregation schemes like MuSig and FROST only became practical after Taproot activated Schnorr in 2021. This nonlinearity matters. People often assume ECDSA and Schnorr are interchangeable. They're not. The mass of Schnorr lets multiple signers collapse into a single signature. ECDSA fundamentally cannot. That single property unlocks an entire class of multi-signature designs. Here's the ECDSA signing equation. S equals K inverse times the quantity hash of M plus D times R, all modulo N. Let's name everything. D is your private key. The hash of M is the message digest, typically SHA 256 of the transaction. N is the order of the CCP 256 K1 curve. K is the nonce, a fresh secret random number you generate for each signature. And R is the x-coordinate of the public point K times G, where G is the generator. Now let's plug in some toy numbers. Let D equal 7, K equals 3, hash equal 11, R equal 5, and N equal 17. First, compute hash plus D times R. That's 11 plus 7 times 5, which is 11 plus 35, equal to 46. Reduce modulo 17. 46 minus 34 is 12. Next, find 3 inverse modulo 17. Since 3 times 6 equals 18, which is 1 modulo 17, 3 inverse is 6. Finally, S equals 6 times 12 modulo 17, which is 72 modulo 17, equal to 4. So the final signature pair R, S is 5, 4. On the wire, that signature pair gets wrapped in DER, the Distinguished Encoding Rules format. The byte stream starts with 0x30, the sequence marker, then total length, then 0x02, the integer marker, followed by the length of R and R itself, typically 32 bytes. Another 0x02, the length of S, then S. Finally, a 1-byte Sighash flag, usually 001, meaning Sighash all, signaling that this signature commits to every input and output in the transaction. That's what you see in raw script 6. The math works perfectly until the nonce doesn't. Suppose you sign two different messages using the same nonce K. Both signatures will share the same R value because R only depends on K. Now watch what happens. The first signature gives S1 equals K inverse times the quantity H1 plus D times R. The second gives S2 equals K inverse times the quantity H2 plus D times R. Subtract the second from the first. The D times R terms cancel, leaving S1 minus S2 equals K inverse times H1 minus H2. Now solve for K equals H1 minus H2. All divided by S1 minus S2. Once you know K, plug it back into the original signing equation, and the private key D falls right out. D equals S1 times K minus H1, all divided by r. 2 signatures, 4 lines of algebra. Total compromise. And this isn't theoretical. It cracked the Sony PlayStation 3 in 2010. It drained Android wallets in 2013 when secure random returned predictable values, and it hit blockchain.info's random number generator in 2014. The fix isn't better randomness, it's no randomness at all. RFC 6979 derives K deterministically by feeding your private key and the message hash into HMAC HA256. Same inputs, same K. Different transactions automatically produce different K values because the message hash differs. Optional extra entropy can still be mixed in for side channel resistance, but it's no longer load-bearing. BIP340 does the analogous thing for Schnorr in Taproot. The lesson. The signing mask doesn't care whether K is random, it cares that K is unique and unpredictable. Determinism gives you both for free. Bad randomness isn't the only way signing can hurt you. The hash you're signing matters too. In legacy Bitcoin before SegWit, signing each input required computing a Sighash, the commitment hash that locks the signature to a specific view of the transaction. The problem? That Sighash recomputed the entire transaction for every input. With n inputs, you serialize and hash the whole transaction n times. That's quadratic work, order n squared. An attacker could craft one giant transaction with thousands of inputs and ping every node on the network for seconds. Validation slows to a crawl. It's a denial of service landmine sitting inside the consensus rules. BIP143, shipped with SegWit in 2017, restructured the Sighash. Instead of rehashing everything per input, it pre-computes 3 mid-state hashes once per transaction. Hash prevals, which commits to all input-out points, hash sequence, which commits to all sequence numbers, and hash outputs, which commits to every output. Each input Sighash now references those 3 pre-computed values, plus its own small per-input data. Total work scales linearly with the number of inputs, order n. A transaction with 1,000 inputs validates 1,000 times faster than legacy under the same load. The DOS vector closes. 3 threads, 3 fixes. Algorithm choice. ECDSA shipped because Schnorr was patent locked, and the Taproot finally activated Schnorr in 2021, closing a loop that opened in 1989. Nonce discipline, RFC 6979, made deterministic K mandatory, so a broken RNG can no longer leak your private key. Hash scaling. BIP143 turned quadratic Sighash into linear, neutralizing a denial of service attack hidden in plain sight. Note what SegWit really did. People remember it for fixing transaction malleability and effectively raising the block size. The Sighash redesign is the equally important third win that rarely gets credit. The deeper lesson is that cryptographic correctness isn't just about the curve being secure. It's about the engineering around the curve, the random number generator, the byte serialization, the hash structure, the deterministic nonce. Get any of those wrong and the math underneath stops protecting you. Bitcoin had to learn that the hard way.